Hello, I am Ritvik and welcome to this presentation on DSMC simulation of rarefied Rayleigh flow. So the outline of the presentation is to show the project objective, the domain, the boundary conditions, the implementation of the method, the results, and the conclusions. So this is a brief project overview. The DSMC method is used for rarefied flow, especially when the continuum assumption is no longer valid, and it solves the Boltzmann equation by the Monte Carlo method. The expected outcomes of the project are to obtain the statistically averaged velocity distribution, to benchmark the solution with the analytical solution, and to analyze the effect of simulation parameters on the numerical solution. So this is a representation of the domain. We have a specularly reflecting wall at the top, a thermal wall at the bottom, maintained at constant temperature of TW, and it is assigned an impulsive velocity along the positive y direction at time t is equal to 0 with a value of 0.2, which is a subsonic case. 50 number of cells are selected and 50,000 particles are simulated. So this is an overview of the implementation of the DSMC method. There are three main steps: the drift, the wall collisions, and the particle-particle collisions. So the drift is pretty straightforward. We stream the velocity particles according to their velocities in the x, y, and z direction. The particles undergo specular reflection at the top wall. So this is a code snippet for the top wall, where when the value of the z increases beyond the LZ, which is the domain, we assign the points, the trajectory onto the variable top, and we get the time after the collision from this relation as implemented in the code here, and then we reverse the velocities upon impact. At the bottom wall, the particle velocity is reset to a biased Maxwellian. Since there's a temperature of TW at the bottom wall, we use these relations to get the velocities after collision with the bottom wall. And R and RG are obtained from the Python libraries for the normal distribution with variance of 1 and a mean of 0. Collision is generally implemented using this equation. However, since this is extremely computationally expensive, since there are two summations in the denominator, a simplified acceptance rejection scheme is used. So here only particles in the same cell are allowed to collide, and they are randomly selected pairs which follow this condition, that is the absolute value of the relative velocities over the maximum value of the relative velocity must be greater than r. And if it's accepted, they are allowed to collide, or else they are rejected and they move on to the next pair, and so on. So the number of candidate pairs for collision are obtained by this formula. And post-collision, since we consider hard body collision, momentum and energy are conserved, and the angles are fixed according to the spherical coordinate system. So we have sine theta cos phi, sine theta sine phi, and cos theta. And these values for the post-collision velocities are implemented in the code snippets shown below. An important thing to note is the relative velocity, the maximum value of the relative velocity has to be overestimated, since it gives more number of candidates for collision as well. However, they must not be so high, as if we have an extremely high value of VR max from the previous slide, by the acceptance rejection scheme, a higher number of particles would be rejected as well. Now, since this is extremely computationally expensive, a parallelization method is required. So Python's multi-processing toolkit and pool functions are extremely useful in this case. So we start and we initialize the parameters. We divide the simulation into independent tasks. We create a pool of worker processes and distribute the tasks to the worker processes. And these worker processes carry out the simulations independently. And at the end of the simulations, all of the results are collected and averaged to obtain the final results. So these are the results. So this is a snapshot of the particle distribution, and the line shows the average velocities of the particles. And you can see that at the wall at some time we have an effect of 0.2, which is due to the wall moving along the positive y direction. And this is the analytical solution given by the Boltzmann equation under the BGK approximation. So this is a Bessel function of the first kind, and this can be evaluated using Python as shown here. Now this is a time lapse of the particles. The particle trajectories in the 2D slice are shown. The particle sizes and the cell sizes and the number of particles are increased for the three cases, and these are pretty computationally expensive, which is why the parallelization algorithm is extremely effective in this case. As we can see, when the simulation starts out, the effect of the moving ball is not felt by the particles, as you can see here. However, as the simulation progresses, we have some sort of effect of the particles here, and we can see that the wall velocity is pretty dominant at later time steps. And this is same case here, and the velocity average shows that the distribution is affected by more by the fluctuations in the velocity when the number of particles are high. And this is a comparison for various cases when we have uh, number of cells as just 50, which is the lowest case. You can see it is in agreement with the analytical solution. However, it's a bit off due to the lower number of particles. However, the points are matching the trend. As we increase the number of simulations, it tends to match the curve more. And as we increase the number of particles, it becomes extremely close to the analytical solution. And these two graphs are for the super high resolution cases when we have 1,000 cells and 10 to the power 6 particles and run over 20 simulations and 50 simulations. You can see they are pretty close to the actual analytical solution from BGK theory. And this is a table for the effect of simulation parameters. So as we see, if we increase the number of simulation runs and average them, we get lower RMS error due to the statistical nature of the simulation. And as we vary the number of cells and increase the number of cells, the RMS error decreases drastically as well. And the same has been applied for a supersonic case. As you can see, a shock front is generated due to the velocity of the particles being higher than the velocity of the speed of sound or the speed of sound, and the wavefront progresses from time t is equal to 0, and we see the particles moving in sort of a direction constrained by the shock. So the DSMC method, and it satisfies the analytical solution quite closely. So the DSMC method is quite effective in solving rarefied problems in highly compressible systems, such as in supersonic and hypersonic cases. So the conclusion is that the DSMC method was able to simulate the Rayleigh flow. For subsonic and supersonic cases, parallelization is used to decrease computational time, and a comparison of numerical results with analytical solution shows good agreement for both cases, and the analyzed effects of the number of simulations and number of cells on the error are also studied. And the scopes for improvement are collision parallelization, use of the variable hard sphere model for better accuracy, and advanced seeding algorithms to reduce noise. And so these are the main references used for the simulation. And yeah, thank you.